circuit. In CR circuit, we shall be talking about the transient charge, and to obtain transient current, we shall differentiate that instantaneous charge to obtain instantaneous current. The circuit goes as simple that we have a capacitor and resistor connected in series, and when the two-way switch is at position number 1, the battery is connected so that the capacitor is charged. During the time capacitor is charged, current flows to deliver charges to the capacitor, and when the switch is flipped to position number 2, this capacitor is allowed to discharge through the resistance R, which is appearing in series here. Obviously, the Kirchhoff's voltage law states that the total voltage applied through the battery, one part appears across capacitor and rest across resistor. Now, applying Kirchhoff's voltage law, we have Q by C as potential difference across capacitor and resistance into current, that is by Ohm's law, IR drop across resistor, and the sum of two amounts to total battery potential. Now current can be written as rate of flow of charge, and that makes our differential equation like Q by C R into dQ by dt equal to E. Now here that tricky thing we shall establish that E is equal to Q0 by C is the steady state value of charge. Q0 is the steady state value of charge which is determined by the battery potential and the capacitance of the capacitor. Now the moment we substitute this, our differential equation is ready for exploring the variable separation method, and immediately after one integration we can obtain the solution of it. The already discussed method for LR circuit, we are going on the same path. There is no great difference, only the parameters are different. So here to this differential equation we shall have separation of variables method. So dq of t equal to q0 minus q of t equal to 1 upon cr times dt. Now I shall multiply the equation by -1 so that derivative of the denominator appears on the numerator. So this is something like a minus x, and derivative of a minus x is -1, that is appearing here, and then we can integrate exploring the same formula. Integration f dash upon f dx is equal to log of f, and we obtain this equation. Here a constant of integration appears. Now this is to be sorted out from the boundary condition, and the physical situation tells that at t equal to 0 there was no charge on the capacitor, there was no flow of charge in the circuit, and therefore q of 0 is equal to 0. By substituting this boundary condition in this equation, we can obtain k, and k appears to be log of q0 because charge is 0, time is 0, only log of q0 is a non-vanishing component in this equation, and by substituting that k1 we get last equation appearing on the screen. Then we have to collect the terms together for q of t on left hand side, and that is the quantity we want to know, so we place it on left hand side, and a simple mathematical rearrangement leads you to the last equation q0 inside bracket 1 minus e to the power minus t upon rc. So here you can substitute that q0 back in terms of e and c, and now this bracketed equation is in terms of all parameters which are involved in the circuit. Now the interpretation of this equation, we shall substitute t equal to 0, and then q of 0 we have to find. Here I should substitute that t equal to 0, and EC inside bracket 1 minus 1 upon e to the power When you substitute 0, it is left to e to the power 0. Anything raised to 0 is 1. 1 upon 1 is 1. 1 minus 1 is 0. So the first prima facie reflection of this equation goes hand in hand with the boundary condition. The second boundary situation is when t is infinitely large, that is steady state value. There is no change in q after that time, that we call a longer time in terms of infinity, and that q of infinity is equal to EC inside bracket 1 minus 1 upon e to the power infinity. So e to the power infinity is infinity, and 1 upon infinity is 0, and here we are left with EC, that is Q0. So this is the steady state value of the charge. The third and the most important boundary condition is that T equal to CR, so that in this term e to the power T upon RC becomes unity, and we get EC inside bracket 1 minus 1 upon E. So EC into bracket 1 minus 1 upon 2.718. If you evaluate this bracket, this turns out to be 0.632, like in LR circuit, times Q0. So this is the CR time constant of the circuit, and we shall now define CR time, T equal to C times R, that value of C and R, such that the instantaneous charge in the circuit rises to 63.2% of its full charge. Now friends, the same thing I am talking about CR time constant. Let us consider that we have a battery that offers us 1 volts, and we have a series resistance of 10 kilo ohms and capacitor of 50 microfarads. You can choose any values and you can calculate CR product, that turns out to be 0.5 second. It means that it will take only 0.5 seconds to raise the transient charge in the circuit to 63.2% of its steady state value. So here, this is a precise plot of the same numerical values being considered, and instantaneous charge in the circuit is represented by this equation, which we have obtained as solution of the differential equation. Now we shall study the decay in CR circuit, and the only thing is that we have flipped the switch to position number 2 and battery is withdrawn, and capacitor is short circuited through resistance R. So as there is no battery, potential across capacitor and potential across resistor sum together should vanish, and it can be written in form Q by C is potential difference across capacitor, R into I. Ohm's law gives us the drop across resistance, and current is to be replaced by dq by dt. Same steady charge condition I am using because I have charged the capacitor using the battery E. So the steady state value of the charge Q0 is equal to EC, and Q of t, this equation after multiplying by C becomes Q of t equal to C into R, dq by dt equal to 0. This is a simple differential equation. It's a very obvious separation of variables you can conduct, and by one integration you can obtain this solution of the differential equation. Here another constant is appearing, which can be evaluated from the physical situation, that at t equal to 0, when we flip the switch from position number 1 to position number 2, the charge in the circuit was Q0, which we call steady state value of the charge. Now substituting Q of 0 is equal to Q0, we get K2 equal to log of Q0, because by substituting t equal to 0, this term vanishes, and this equation can be rearranged properly to look like a standard equation, Q of t equal to Q0 into e to the power t upon minus t upon RC. So here I am precisely writing the exponential term in the denominator so that I want to substitute different values of t and pick up a gist of what is happening. Now at t equal to 0, in this equation if you substitute t equal to 0, e to the power 0 will be 1 and q of t is equal to ec, which you call q0. At t equal to infinity, q of infinity is equal to ec 1 upon e to the power infinity. Anything raised to infinity will be infinity and this term will be infinity. 1 upon infinity will be 0, and after a long time the instantaneous charge in the circuit will diminish to 0 value. It has asymptotic behavior on the time graph. At t equal to cr, very important situation, we have q of t equal to ec into 1 upon e, and that becomes 0.367 times q0. So cr time constant now we can define as the time which takes uh, the instantaneous charge in the circuit to 36.7% of its full value. For the same numerical situation in which we have opted a battery of 1 volt, resistance of 10 kilo ohms and capacitance of 50 microfarad, obviously it will be 0.5 seconds time to decay the charge to 36.7% of its steady state value. So this is a plot developed in the maple from this equation for given values of E, C, R, and time is rolling from 0 to 5. This is a plot in which we have made transient current growth as well as decay at the same time, and this is a very symmetric kind of plot you can observe, and at that RC time constant, the obvious values you can figure out in this diagram. Now these things together we have considered, but if someone likes to discuss the equation in terms of transient current in place of transient charge, you have to differentiate the charge equation so that you can get the instantaneous current in the circuit. Now let us do that. It's a very simple thing. We can quickly reach to that. Okay. For obtaining current, we have to differentiate with respect to time. The derivative of 1 will be 0, and e to the power function will be function times e to the power function. Sorry, f dash times e to the power function. So derivative of minus t upon cr, we have minus 1 upon cr, and by simplifying that we get e upon r times e to the power minus t upon rc. So you can call e upon r as I0. Similarly, here if we differentiate this equation, e to the power function, so sorry, e to the power function will be f dash times e to the power function, and minus term will appear here, and this minus term has a typical significance that one can understand as current will be flowing in the opposite direction. I mean to say that when charging was taking place, current was going in a clockwise direction uh, or whatever direction, and during discharge it will be in opposite direction. That is the gist of it. Now here I have tried to show you transient current on left hand side graph. This is rising transient current and this is decaying transient current, whereas in the next diagram we have transient current. So the y parameter is a little different, which is obtained from derivative as in the earlier slide, and during discharge current is flowing in opposite direction. So this blue graph is for charging and the red graph is for discharge. So this makes a complete sense of this flow of current as well as transient charge in RC circuit. And these are the basic things. I shall begin from the differential equation 1. ODE1 I shall call Q of t by C plus R into first derivative of Q of t with respect to time. That's equal to V. Here I have used V in place of E like in the earlier discussion. Now the boundary condition is Q of 0 is equal to 0. So D solve ODE1 for BC1 will give us the necessary solution, and you can sublime the boundary conditions that V is equal to 1, R is equal to 10K, and this is 50 microfarad in solution number 1, and we obtained this equation. Obviously RC time constant is 0.5 seconds. Now here the command PLOT, the right hand side of solution 1 for the range 0 to 5 seconds will render us this plot, and we can develop a grid to see what happens at 0.5 seconds. And here you can see that the 63.2% of the maximum value is attained here. Similarly, we can discuss one more situation where voltage is 1, R is 2 ohms, and capacitor is 0.005 farad. So for this situation, RC time constant is 0.01 second. So instead of X rolling from 0 to 5, we have to opt T rolling from 0 to 0.05, and here we can have a plot. RC time constant is 0.01, and here 63.2% of value is attained here. Now we shall go through the decay process, and the differential equation we have to replace E by 0 because there is no battery and we are offering a short circuit situation, and the beginning point is where the charge is Q0, that is equal to EC or VC, whatever you call. So t equal to 0 is the beginning time. So D solve ODE2 for BC2 will render us this solution, which we have already done, and you can substitute V equal to 1, R equal to 10,000, and capacitor 50 microfarad in solution 2, and you can make a plot of right hand side of this equation solution 2.1 for the range 0 to 5, and you can see the RC time constant is 0.5, so 36.7% of decay occurs in the first half second. Now second situation where R is 2 ohms and 5 C is 0.005 farad. So a similar graph offers decay, and in 0.01 seconds 36.2% of the charge is disintegrated. These two plots can be seen together, and you can make out the values for 0.5 seconds. For second situation also you can make out the situation for 0.01 second. Now for currents you need to differentiate the equation. Here we shall differentiate solution 1 with respect to time, right hand side of solution, and that is being called I of t. This I am calling as SOLNA. So this offers same equation which we have discussed in the PowerPoint presentation, and we can substitute. Similarly, we can differentiate the equation solution 1.1, which was for numerical values of first set of constants, and we get this equation. This can be considered for plotting. So plot right hand side of solution A1. So after substituting that V equal to 1 and value of resistance and capacitor, we get current. Now see, the moment key is placed in the position number 1, full current goes through the circuit, and as the capacitor is charged, the current is reducing. So when the capacitor is fully charged, there is no flow of current. So saturated value of charge is there, that we call Q0, and when the saturation value of full charge is obtained, that time current in the circuit is zero. This is the tricky thing that one has to understand. During decay process, we have that solution 2, and you can differentiate that solution 2 right hand side with respect to time to get the decay current. And for first set of constants, you can consider solution 2(1), which is in numerical sense, and this can be considered for plotting. And here we have used a command plot right hand side of solution B1 for time range 0 to 5 seconds, and here you can see that the current is being shown in the negative direction, which is because it is opposite to the charging current. So these two graphs, if you like, you can see together by making a plot command in the parenthesis right hand side of solution SOLN A1 comma right hand side of SOLN B1 for the same time range. So this is a very symmetric and nice thing you can observe. Thank you so much for your patient listening. But before closing, I want to quickly go through the LCR circuit. And in Maple video lecture number 6, I have discussed the complete theory. If someone is interested in listening to the whole discussion of solving differential equation, which is of second order, you can refer to that video, Maple lecture number 6. And here I shall narrate you a different way of handling this problem of growth and decay of current in LCR circuit. And here we have E equal to 5, that battery potential I have set to 5. P is some scaling parameter, I have selected 1 upon 500. Capacitance is 0.19 microfarad, resistance is 50 ohms, inductor is 10 to the power minus 3, that is 1 millihenry. So these are the values assigned. So first differential equation which appears from the basic circuit applying Kirchhoff's voltage law looks like this. Here we have second order derivative accommodated through $2, and output I have not displayed by placing colon. Solution 1, we have desolve command for equation 1, this equation. The boundary condition Q1 for first situation Q1 at t equal to 0 is 0, and current, that is derivative of Q1 at t equal to 0 is 0. This is being solved for Q1, which is function of time. The output is again suppressed, it's not displayed. If you like, you can use a semicolon instead of colon. And here I have used a command assign inside bracket SOLN1. So this is assigned for plotting, and later on we shall recall the plot command. Second situation, in which Q of Q2, which is function of time, by C, first order derivative of Q2 with respect to time into 10 times R plus L into second order derivative of Q of t. Second order derivative is encompassed through this command $2, that's equal to the battery potential. Again, this differential equation is solved, it is assigned value solution 2. In the same fashion, this is the third differential equation we have, Q3 function of time by C, first time derivative into 2 under root of L by C. You have to refer to that video lecture number 6, Maple video lecture number 6 for these differential equations. This we have 3 solutions. All 3 solutions are assigned through assign command, and I am using protocol with plots. P1 is plot for Q1, color is set red. P2 is plot for second differential equation color set is blue, and P3 is plot for Q3 function of time, which is set in green color. Now these are the three different cases occurring in that second order partial differential equation for LCR circuit, and these three we can display through P1, P2, P3, and the axis type box we have selected. So these are the three different cases. This is the third condition in which the fluctuation of charge takes place because of the capacitor charging. Similarly, for decay, we can have different boundary conditions, and for that we have gone through the another set of the plots, and they can be displayed together. Here this is x-axis, and the capacitor will discharge through the resistor and inductor, and it will go on fluctuating like this, and then will approach to zero. If resistance is made zero, then this fluctuation will be of same amplitude. There will not be any decay in that.